Okay, we are going to be looking at exponential functions and their graphs in this lesson. What I want to quickly go through are the different types of functions that we've talked about so far this semester. The first one is a linear function. The graph of that is a line. For example, y equals 2x plus 3. Again, the graph is a straight line. That's what we started the semester with. In the second unit, we talked about quadratic functions. So, for example, y equals x squared plus 3. The graph of a quadratic is a parabola. And then what we're talking about today are exponential functions and their graphs. For example, y equals 2 times 3 to the x. And so the graph of this is, well, that's what we're looking at today. So as it says, we've focused on linear and quadratic functions so far, so let's take another look at exponential functions. In general, an exponential function is f of x equals b to the x. Couple of notes here that b is the base. That has to be a positive real number other than 1. Other than 1. And then the x, that's the exponent. The exponent is any real number. All right, what we're going to do is graph the following functions on the same grid using points from the table of values that we are going to create here. We are going to take note of each graph's y-intercept and then also how close it is to the x and the y-axis. So I'm going to kind of go through getting these y-coordinates pretty quickly, but all you're really doing here, for example, in the first one, to get the y value, when x is -1, we would take that -1, put it up in the exponent of 3. So what this is y equals 3 to the -1st. Well, to make a negative exponent positive, we put it in the denominator. So this is y equals 1/3. So the value of y is 1/3. For 0, this is 3 to the 0, which is 1. And then when x is 1, so that's 3 to the 1st, which is 3. So now we have a few ordered pairs that we can graph. The first one is -1 1/3. So on my graph, I'll plot -1 1/3, and you can kind of guesstimate where that would be. The next point is 0 1, and the third point is 1 3. So from that, we'll draw in and kind of follow those graphs. All right, we'll do a similar thing for the second function, y equals 2 to the x. So if we plug a -1 in for x, that's 2 to the -1st. Make the negative exponent positive by putting it in the denominator. So that's 1/2. 2 to the 0 is 1, and 2 to the 1st is 2. So now we have 3 points that we can plot. The first one is -1 1/2. So -1 1/2, that's a little bit above the -1 1/3. We have 0 1 again, and 1 2. Draw that in. And then finally, we'll do a similar type of thing for the last one. Doing the same thing to get the y values, we're just plugging in the x values into the exponent. So the y values here are about 0.7, 1, and 1.5. Let's plot those. So -1.7 will be above the other three. 0, 1 again is on that point, and 1, 1.5. All right, so a couple of things that we're seeing here that we need to take note of. The y-intercept of all three of these is at 0, 1. The other thing that we want to be noticing is, if you look at the pink line, that's the first one we did, that base was a base of 3. That one's growing the quickest. So the larger the base, the quicker it grows. Okay. These are all examples of exponential growth. All examples of exponential growth. All right, similar type of thing. We are going to get a table of values, plot them. I'd like for you to try this part on your own, and then you can come back and make sure that you've done this correctly. So now take a look to make sure that all of your y values for each of these functions is correct and that you've graphed this correctly. Couple observations again, all y-intercepts are 0, 1. This time, the smaller the base, the closer the graph is to the x and y axes. Okay. A couple of discussion questions that we should have been seeing from these two examples. For what values of b does the graph rise from left to right? So we saw for any values of b bigger than 1, this is exponential growth. And then for any values of b that are less than 1, but remember we have to be bigger than 0, this is exponential decay, meaning it goes down left to right. So exponential decay, exponential growth. Depends on your values of b. All right, so what we're going to do on these last few examples is we are going to tell whether each of these functions is exponential growth or decay, and then we will graph it. So for the first one, look at your value of b, 3 over 2. Is that bigger than 1, or is that between 0 and 1? Well, that is bigger than 1, so this is exponential growth. The other thing that we need to be able to say is that the y-intercept is 0, 1. Basically what you need to know is that the number in front of your base is your y-intercept. Well, you can think about there being a 1 in front of your base for this one. That's why our y-intercept is 1. So if we were to graph this then, we know that we can start by plotting the y-intercept at 0, 1. And then all you would do is plug in a few other points to get some other points. So kind of similar to what we did with the table. So if I plug in -1 to this x, my y value would be 2/3. So -1, 2/3. If I plug in +1, my y value is 3/2. So that's 1.5. So that gives me a couple of points that I need so I can sketch the graph. For the second one, look at your value of b. Because that is between 0 and 1, this is exponential decay. And then the y-intercept, look at the number for the base. So the y-intercept here is 0, 6, 0, 6. So on your graph, you would plot the y-intercept at 0, 6, and then get a few more points. This doesn't fit very well on our graph, but it decays pretty quickly. All right, the very last thing that we are going to look at is compound interest. This is simply using a formula, A equals capital P times 1 plus R over N to the NT. Now we need to talk about what those different variables mean. The P is the principal or the initial amount that you invest. R is your rate written as a decimal. N is the number of compounds. And then T is the number of years that you have invested. So if we look at the first example, we're only going to do annually. Actually, we'll do annually and monthly, and then I'll have you do daily on your own. So if we are finding the final amount of a $500 investment, that's our principal, how much we're putting in. After 8 years, that's your value of T. At 7%, that's your R, but we need to write that as a decimal, so 0.07 compounded annually. So the number of times a year annually is 1 time a year. That's your T. So it's just a matter of plugging this into the compound interest formula. A equals 500 times 1 plus 0.07 over, this should be N, not T. The number of times we compound is N. My bad. N is 1. And then to the 1 times T is 8. And then it's just a matter of putting all of this in your calculator. You need to do this part first, and then to the exponent, and then times 500 at the very end. Make sure that you know how to calculate this on your calculator. You should be getting $859.09. If we do a similar thing, but this time compounded monthly, that means the number of compounds in a year is 12. So the only thing that changes here is the value of N. So instead of 1, the value of N is now 12 to the 12 times 8. Again, make sure you can enter this correctly on your calculator. We should get 873.91. All right, I'd like you to do the daily on your own. So the number of compounds this time is 365. You should have gotten 875.29 cents. So make sure you can do that on your calculators.